Alright, hey folks, we're going to take a look at light and how light bends through a process known as refraction. Now, what refraction is, right? Refraction is the bending of any sort of a wave, right? It doesn't have to be light, but we're going to specifically look at it in terms of light, as that wave goes from one medium to another. Now, this only happens in two situations, right? This happens when the medium has a different, what is known as index of refraction, right? So we have two different mediums that are going to have light move, or any wave move in different speeds throughout it, and it has to move at an angle. So if you notice in the simulation to the right hand side here, we see light coming in at some angle measured from the normal. We're going to treat the normal the same way that we did in light reflection, that it's perpendicular to the surface where that incident light makes contact. But now that light's able to pass through and go into a new medium, which means it's going to take a different path because that light is moving at a different speed. Now, as light bends, right, light either bends towards or away from that normal, depending on whether it started fast and gets slow or starts slow and gets fast, right? The order does matter here. So if you're in a slower medium, that light is going to bend towards the normal. So on the left-hand side, what you'll see is we have a faster medium on top, slower medium on the bottom. The incident angle, theta I, is greater than the refracted angle, theta R. So when light slows down, it bends towards that normal. For our fast medium on the right-hand side, here we have light in a slow medium on top, moving into a faster medium. So our incident angle, theta I, with respect to normal, is less than theta R, our refracted, in our faster medium. So when light speeds up, it bends away from normal. When light slows down, it bends towards normal. So what we observe is the angle in the slower medium is always going to be less than the angle in the faster medium. And now how much this bends depends on what's known as the index of refraction. So our formula for this is N, representing the index of refraction, equals C over V. So the speed of light in a vacuum, which is that 3 times 10 to the 8th meters per second, divided by the velocity of light within the medium itself. So basically, you're taking how fast would light move in a vacuum, how fast is light actually moving in this medium, and the ratio that you get is the index of refraction. So if you have a high index of refraction, so if that N value is high, think about the math that needs to happen here. That velocity has to be very low, right? The smaller N gets, the faster light is moving within that medium relative to the speed of light. The lowest that the index of refraction can be is 1, because that would be light in a vacuum then continuing to move in a vacuum, right? So the medium would be a vacuum itself, so you'd end up with C over C, which would get you 1. So the faster light moves, the lower the index of refraction is. The slower light moves, the higher the index of refraction is. And because we're ratioing out these velocities here, there is no unit on N. Looking at the indexes of refractions here, you kind of go, okay, great. So materials are going to have some different index of refraction. I'm looking at the table here. Ice is 1.31. Water at 20 degrees Celsius is 1.33. You know, you've got crown glass, which is 1.52, and you've got flint glass at 1.57. You've got diamond at 2.417. So everything has a different index because light's going to travel at different speeds through different substances. If you want to really get light to bend, you want to have a larger difference within those indexes of refraction. So it's not so much saying, well, if it's higher, it's really a matter of what's the difference between the two. So if you take light going from air to water, and we'll just call air 1 and water is 1.33, the difference there is 0.33 between the N values. Well, if we take a diamond and put that diamond in air, now your difference, air is 1, diamond is 2.417. The difference there is 1.417. That's a large difference in the N values. So we're going to see a greater effect of that light bending from air to a diamond as opposed to air into water. The law that we use to abide by this is known as Snell's law. So we basically take what's happening refraction-wise in one substance, so the original medium, and then what's happening refraction-wise in the second medium, right, in our new medium. So n1 sine theta 1 equals n2 sine theta 2. So basically, the subscript 1 is telling us this is our original, this is our first substance that light was in. N2 is telling us this is our refractive, or the subscript 2 is telling us this is our refractive material, or the second medium that it's moving through. So it starts in medium 1, it ends in medium 2. So we can use this law to predict either what is the index of refraction of a material if we don't know it, or we can predict the angle that that light is going to move as it passes from one material to the other. And again, what we see here is that the bigger the difference in those n values is, the bigger we're going to see these angles, right? Or the bigger difference we're going to see in these angles. And again, our high index of refraction tells us it's a small angle. Small index of refraction tells us it's a large angle, right? And that larger angle is going to be the higher speed substance. The smaller angle is going to be the slower speed substance. And throughout all of this, right, we're still going to obey some law of reflection. So light, not 100% of the light's going to transmit through. There's going to be a small percentage of light that's going to reflect. I mean, think about looking into a pond or looking into a lake. Yeah, you can see down into the water, but you're still getting some of the reflections coming off of it, which allow you to see the trees up above and the clouds and whatnot. So this isn't always a 100% thing. You're still going to get some light that's reflected. Now, what ends up happening is that your light can only bend away so far. If you think back to those diagrams earlier in the presentation, as it bends towards, it's eventually going to get to the normal, and then it's going to stop, right? So you're still going to see that light, but it's going to bend as much as it can. Well, when light gets faster and bends away from normal, eventually it can't bend away anymore because it reaches the surface interface between the two mediums. When this occurs, we get what's known as total internal reflection, which means the light actually doesn't escape into the second medium. Rather, it travels from medium 1, makes contact with the surface, and then reflects back down, obeying the law of reflection, into medium 1. So we get no light to go into medium 2. It all stays within medium 1. This only happens when you're going from a high index of refraction to a low index of refraction. So if your light is speeding up is when we will see this occur. If light is slowing down, we do not see this happen. And depending on what your two mediums are, there's what's known as this critical angle that exists, where if the angle of incidence is greater than that critical angle for the two materials, this is when we'll see that total internal reflection. So this doesn't always happen as light speeds up. It happens only under certain conditions. So here's an example. Like if we send light straight on at 0 degrees, that light's going to pass through, it's not going to bend. Because remember, to get refraction, the light itself has to show up at an angle. Well, eventually, what we see here is incident light at 15, 30, 45, and 60 degrees that refracted, right? We're at 20, 42, 70 degrees respectively. Well, at some point, it can't continue to bend, so it reflects within. So what we see at the 60-degree mark is that total internal reflection. So the incident ray and the reflected ray will each be at 60 degrees. Our blue region is representing the high index, so the slower speed. The white region is representing the lower index, or the higher speed substance. Right, as that light speeds up, it continues to bend more and more until it can't bend anymore, so it all gets reflected. How we find this critical angle, right? So we assume that when that light refracts, it's going to be perpendicular to the normal. So it's going to be 90 degrees, which is going to put it directly on that interface between the two mediums. So if you look through the proof on this here, right, your theta 1 is your critical angle. Your refracted angle is now defined to be 90 degrees. When we go through and work the math, we end up finding that the sine of the critical angle is n2 over n1. Which means if you want to find what the actual critical angle is, you need to take an inverse sine of n2 over n1 in order to find theta c. But the bottom right-hand corner, that sine theta c equals n2 over n1, that is our formula to help us get to the critical angle to figure out, hey, is this incident light actually going to pass through, or is it going to have total internal reflection?